What we're working on today is parent functions. We've already worked with one parent function. It was y equals x squared. In function notation, that was f of x equals x squared. And remember that these are called quadratic functions, but we usually call the shape a parabola. Let's look at the keys to graphing these functions. Remember that we started at the vertex, and for the parent function, the vertex was 0, 0. And then from there, we moved over 1 and up 1, over 2 and up 4, over 3 and up 9. So to create that graph, we'll put our vertex at 0, 0, and then go over 1 and up 1, and then back to the vertex, over 2, up 4, and on the other side as well, and back to the vertex, over 3 and up 9. Then we want to connect those dots with a smooth curve that is not pointed at the end. Go all the way to the edge of your graph paper and get arrows on there. The domain for this function was negative infinity to infinity as we scan left to right. And for the parent function, the range, as you go from bottom to top, starts at 0 and goes to infinity. So the range was 0 to infinity. As we move left to right, let's look at increasing and decreasing. This function is decreasing when we start at negative infinity until right here, which is x equals 0, and then it begins increasing towards positive infinity. So it was decreasing from negative infinity to 0, and then increasing from 0 to infinity. This graph is positive. It looks like everywhere, except you have to realize that 0 is not really positive or negative, so it's positive everywhere except 0. And we write that in interval notation by going from negative infinity to 0, and then skipping over 0 and starting back up and going to positive infinity. And this graph is negative nowhere. And we have two more categories that we need to talk about, symmetry and even and odd function. So we're going to take a few notes on the back of our packet about symmetry and even odd functions. There are two types of symmetry that we're going to talk about with regards to functions. We could have y-axis symmetry. In y-axis symmetry, what you would have would be a graph that could be reflected across the y-axis. So an example would be something that looks like a capital M maybe. If I drew it correctly, then I could fold this half directly over onto that half, and that would cause me to have y-axis symmetry. Now in y-axis symmetry, each ordered pair has a partner on the other side. So if I call this ordered pair x, y, then the partner on this side would be the ordered pair negative x, positive y. So negative x, y. So in y-axis symmetry, our partner points are xy and negative xy. Y-axis symmetry functions are also called even functions. So if it has y-axis symmetry, it is an even function. The other type of symmetry that we're going to talk about is origin symmetry. Origin symmetry is really 180-degree rotational symmetry. So if I were to draw a graph, it's a weird looking graph, I know. But if I take my paper and I rotate it at the origin 180 degrees, then my graph would look exactly the same. So that's how we know if a graph has origin symmetry. It's that 180 degree rotation. So if we label these partner, these matching points, if this ordered pair is xy, then the partner point would be, instead of positive x, it would be over at negative x. And instead of going up y units, we'd be going down y units. So this partner point is negative x, negative y. So in origin symmetry, the partner points are xy and negative x, negative y. And if you have a function with origin symmetry, it is considered to be an odd function. So those are our two types of symmetries and our two types of functions, even and odd. So let's go back and answer those questions for our parabola. Looking at this parabola, you can see that it has it has symmetry across the y-axis. So its symmetry is y-axis symmetry. And when we just talked about y-axis symmetry, we said that if it has y-axis symmetry, it is an even function. So this is an even function. And that's your parabola family. Let's move on to the next family of functions. The next family is going to be the square root family. The parent equation for the square root is y equals square root of x. And in function notation, that would just be f of x equals square root of x. I want to build this function. I want to tell you the keys to graphing it, and then we'll look at all the other aspects. The keys to graphing a square root function, just like we did with the squaring function, the quadratic function, we're going to start at the vertex. Well, it's not really a vertex, so I won't call it that. We're going to start at 0, 0, really. So we're going to put a point at 0, 0. Now, if you think about the equation, the square root of x, the next value that I'd want to put in for x would be the perfect square. So I'm going to go over to 1 on the x-coordinate. If I put x in, when I take the square root of it, I get 1 out for y. So I would go over 1 and up 1. So that would be my next point. Now the next value that I'd want to take the square root of would be 4, because 4 is a perfect square. And if I put the square root of 4, I'm going to get out a 2. So I would go from the vertex over 4 up 2. Then the next value I'd want to put in would be a perfect square, the perfect square of 9. So if I take the square root of 9, that's going to give me a y value of positive 3. So I will go back to the vertex and I go over 9 units, up 3 units. And this is the shape of that graph. It kind of looks like a sideways parabola. I sort of think it looks like an eyebrow. You can nickname it what you want, but I usually call it the eyebrow graph. The domain for the eyebrow graph, if we scan from left to right, the very first x value that hits the graph is 0. And since it has a closed dot at 0, our domain has a bracket at 0, and then it continues on to infinity in the positive direction, so it will go from 0 to infinity. Now the range, we're going to scan bottom to top. So starting at negative infinity, there's no graph until I get to this y value right here, which is 0. So the range will go from 0. Now notice that this graph continues to grow. So it does eventually continue growing, so our range also goes to positive infinity. Now let's check for symmetry. The types of symmetry we had were y-axis symmetry, where I would fold the graph over the y-axis. This graph does not have that. The other was origin symmetry, where if I rotate 180 degrees, the graph looks identical, but that doesn't work either. So our graph is going to have no symmetry. And since it has no symmetry, it is not even or odd, so it is neither. Let's look at where this graph is increasing and decreasing. As I go from negative infinity to infinity, the graph is doing nothing out here because it doesn't exist. It starts at 0. And as I go from left to right, from 0 towards positive infinity, this graph is rising. So my graph is actually increasing from 0 to infinity. And it just keeps going and going and going in that positive direction. So it's decreasing nowhere. Positive and negative. Again, positive is above the x-axis. So this graph is above the x-axis everywhere from 0 to infinity. And negative is below the x-axis. And that never happens. So it is negative nowhere. And there's your square root function.